Okay, so what we're dealing with here are polynomials. That's what Module 4 is all about. We're dealing with things that look like wavy curves when we graph them. So when you see a polynomial that's in this format, this is in factored form, I want you to think about what this form tells you about what that graph is going to potentially look like. So what do we know about what the graph may look like based on this form? Do we know any of the zeros, which are x-intercepts? Could we know any y-intercepts? Could we identify how many waves or curves it might have? Is it an even or odd function? Probably one of the easiest things to say is there's a zero at x equals blank. Just imagine like you were going to plug a number into x. Would there be something that's really easy to plug in, for instance? So if we plugged in a 5, what happens? You plug in a 5 there, that gives us 0 squared, and then 5 plus 2 cubed, and 5 plus 4. Like that is going to give me a point. I don't really care what all this stuff is. As long as it zeroes out one of my linear factors, it's going to give me a 0, isn't it? Okay, and then another one that's suggested is -4. If we plug a -4 in, that'll zero that piece out. It'll make these something else. I don't care, but it'll be something times 0 is going to give me 0. And then the last one, if I zero this factor out at -2, that's also going to give me 0. So those are nice, easy points, which tell me a little bit about the graph. Whoops, I kind of have to make a different scale here. Tells me a bit of information about what the graph may look like, in that it's going to cross at 5, 0, -4, 0. These are coordinate points, and -2, 0. So I know that it's going to go through those points. The whole idea behind this module is to identify, like, once you have a polynomial, and usually they're not given in factored form, so that's really what we're working on with the long division. But once you have it in factored form, that helps you see the zeros, which is then culminating towards you being able to sketch approximately as accurately as possible the graph of the function. And obviously you may be thinking, okay, well, I could just put it in the graphing calculator. Yes, you could. These days, that's even easier than it used to be. But our goal, our challenge, is to zoom into the properties of the graph, and to analyze the graph, not just to say, oh, look, I graphed it on this thing, this piece of technology, but more so, like if someone asked you about a part of the graph, you'd actually understand it more deeply than just like, here's a picture, right? So in the process of doing and graphing it, you actually slow down the process so that you can answer questions about it. So the other thing that I know is it's positive, right? So what does that tell me? But I still also need to know a degree. So there's something else. So there's zeros that we can identify, which are actually x-intercepts. And we can also think about what's the far left and far right behavior. And what you do there is you think, okay, if I make my x really, really negative, what's it going to do? And if I make my x really, really positive, what's it going to do? Is it going to get bigger or smaller? And that helps you identify whether it starts here and like waves through and ends here, or if it starts here and waves through and ends here. So that's going to help you with that. So one, you could say, well, what's p of like -1,000? So you'd, want to plug that in. We can also look at the degree of this. Like, so this is a square. This one is a square. This one's a cube, and this one's a fourth. So the zeros, in this case, I have at 5, the one at 5 has multiplicity 2, and you might see that in Alex. Multiplicity 2 means that there was a square on that factor. So what that's going to do on the graph, you'll see later, is it actually will bounce off of the 5 rather than crossing through the 5, because it's kind of like squared. Your other zero, -2, was multiplicity 3. So that was that cube there. And the last 0 was -4, which was multiplicity 1. You don't really have to write a multiplicity if it's a 1, but they will sometimes say list the zeros along with their multiplicities. So rather than writing 5 twice, you just say it's a multiplicity 2. So if you think of that, the leading coefficient, so what is the degree of this polynomial? When I multiply everything out, which is a ton of work, and we're not going to do that, we can imagine that this one's going to have an x squared, and then this one's going to have an x cubed, and this one's going to have an x. So the leading term is going to be x squared times x cubed times x, which is what degree? X squared times x cubed is x to the 5 times x is x to the 6. So this is a degree 6 polynomial. Again, these are all things that, you know, you won't be asked all of this in one question necessarily, but these are all questions that can be asked about the same polynomial. Okay, so if it's a degree 6 polynomial, that means it's an even function because it's an even number. And even functions usually will, like, if they start at the top, they'll end at the top. If they start at the bottom, they'll end at the bottom. So let's just think, like, if you put a really negative number in, I don't really care what that number is, but a very negative number in that first part squared is going to become positive, right? When you cube that very negative number, see if it's a negative 1,000 plus 2 doesn't really make a difference. It's still negative. Cubed, it's going to be a negative. And the negative number without a power is also going to be negative. So when you multiply that all together, you should get a positive number for a very negative number. So the way to write that is for far left behavior would be as x goes to negative infinity, p of x goes to positive infinity, meaning it's starting up high. So what that tells me is it's coming in this way rather than coming in this way, right? So now try and think of what's going to happen at the very far right. So if it was really positive, like really big number, then what sign would you be producing? And usually that's just coming from the leading coefficient. Like, so the degree 6, you could just right away say, if it's degree 6, a very negative number to the power of 6 is going to become a positive number. And a very positive number is also going to result in a very positive number. So it should come in this way and leave this way. So that's what that tells us. So I don't actually have to do all this. I could just look straight at the total degree, assuming that the initial term is positive. The standard form of an even function is going to be starting at the tops for negative infinity and positive infinity. If it was negative, just like a parabola, when it was positive, it was upwards facing. When it was negative, it was downwards facing. Parabola is an even function. So this changes when you have an odd function. Like if it was a degree 5, they would go opposite. Right? Okay, and then the other thing that we know is that a multiplicity 2, so an even multiplicity, will bounce off of a point, and we know that just through trial and error. And an odd multiplicity will pass through. So when I do this, if I want to sketch my graph, once I have my zeros, I can say that I'm going to go through -4. That's going to go through. And so it's going to weave back, and it's going to pass again through -2. The only thing is, as your multiplicities get higher, it gets flatter as it passes through. So it's a little hard to draw this because it's so small, but it would not come in at such a sharp angle. It would actually like flatten through it. And so now it's going to have to weave through that last point, the 5, but It's a multiplicity 2, which is good because what that means is it's going to kind of bounce off of that point. So this is the essence of graph sketching. Like if you're asked to sketch a polynomial graph, obviously first you need to have it in factored form, which is what we're going to work on, of how to get that factored form and how to use long division to do that. Once you have those points, you have just a few more things to think about. And the last thing that you will not learn specifically in this course, but you will just be asked to like identify from a digital graph is like, so what about the minimum and maximum? And there's actually, you'll notice there are minimums and maximums. There's more of them. So if something is not an absolute maximum for the entire function, it's called a relative maximum. Whereas this here is an absolute minimum. Relative just means like relative to its local area, but not overall absolute to the entire function. Okay, so here's a proper sketch of this graph from a graphing utility. So, you know, like I was close. I didn't quite make that. I could have found some more points here to kind of identify where that's going to pass through. But that's the general shape of that graph is there. And then what that helps me do is zoom in at the appropriate places of like where it's going to have, you know, certain maximums and things like that. So that being said, the only piece that is like really quite challenging is if that's not factored, we need to get those zeros because those zeros really help us form the shape of the graph. So now let's look at, let's see here. Okay, this was, yeah, this is the same function. This is just a summary here for you written out. We just did that. So now let's say we have something like this, right? So it's not factored. And for this lesson, we're like really just zooming in on how to find the zeros. And last time I had given you the term to divide by, like let's say divide by x minus 2. And like when you divide it, it might give you the appropriate factorization with a remainder of 0, or you might get a remainder, which means that it doesn't factor by that term exactly, and you might want to try a different term, right? So when you divide this by, say, some random linear factors start with x, and they're binomials, you're kind of guessing, right? Like I could do the long division here. I have no idea if this is going to work or not. But just as a review, because you asked me, like your goal here is to make sure that you have all of these in decreasing exponential form and you're not missing any. So if there's a power of 0, you would make it a 0 term of that type. And then you're trying to put this x minus 2 in here. So you're saying, well, how many of those do I multiply? Well, I have to multiply by an x squared term and by 3 so that this 3x cubed term matches. Right, so I'm multiplying it out by the divisor, and then I'm subtracting. And then, you know, 11 minus negative 6, 11 plus 6, drop the next number. Can everybody see how we chose that 3x squared? Why did I choose 3x squared there? I was looking at those parts. I was thinking, what do I multiply x by to get 3x cubed? So that's what I needed there. And I put it above the x squared so that all of the x squared terms are always like all above each other because you want to preserve place value. So the next one, we want that leading term to be 17x squared. So what do I multiply x by to get 17x squared? Plus 17x minus, and then 17 times 2, what's that, 34? You're minusing all of that, so that means you're going to change that sign, negative 6 plus 34. So that's your 28x. Drop the next one. And, you know, something like this, 28x, and then this is going to be minus 28 times -2. So 28 times 2 is 40 and 16, so 56. And you can see we have a remainder, right? So we just did a whole bunch of work here. And we didn't get something that is a perfect factor of this at all, because now we have a remainder of -8 plus 56. So that's what, 48? So, you'd have to write this as either, so this equals 3x squared plus 17x plus 28 plus 48 has not yet been divided by x minus 2. So this is our remainder. There are easier ways to determine this exact thing. So we learned those last day. One would be to shorten this process and to have the synthetic division process here, which remember was the opposite number there. That's like the result of the zero of the linear factor. And then you drop, multiply by the 2. This is your multiplier. And then you're going to get all these same numbers that you had here. And again, you get your remainder and your resulting polynomial. Okay, so I mean, that was a bit less work, but it's still, didn't really help us factor this. So you could have done that right away. I'm just peeling away all the strategies that you have. Like, what are all the possible strategies you can throw at this problem? Okay, so long division, synthetic division. The other thing we learned last day was the remainder theorem. If you just put 2 in for this polynomial, you should get the remainder. So if I go 3 times 2 cubed plus 11 times 2 squared minus 6 minus 8, 6 times 2, that, whatever that gives me, should give me the remainder. So that's another strategy you have, is I could right away just check, does x minus 2 work as a factor? If it gives me 0 when I plug in a 2, then I know it's a factor. If it gives me something else, that means it has a remainder, and that is the remainder. Okay, so right away, so all of this tells us that x minus 2 is not a factor of p of x, right? Great, you're like, yay, so now what? So now what we want to introduce is, okay, well, we could keep guessing, and we could inevitably use this strategy and wait until we find something that we can plug in here until we get a 0, and then we know what to divide by. So we don't have to do any of that division until we know it's going to be a factor. One way to do that is to take a graphing calculator. I have this fake graphing calculator on, this is actually an app. It's called, it was free, I just found it today. It was called Graph N Calc 83, right at the bottom there. It does a similar job as your TI 83 would, like your regular kind of basic one. What's nice about this that is less easy with Desmos is that when you have your function typed in, I think I typed this one in, this blue one, this last one here, 3x cubed plus 11x squared minus 6x minus 8, that was the one we're working with. I can, rather than going 3 times 2 cubed plus 11 times 2 squared minus 6 times 2 minus 8, and then let's check another number. We're going to have to check quite a few numbers potentially. So what's nice is you go to table, and if on your graphing calculator, if you have one of these, or you could use this app once you have it, you can always go to second table set. If this table is already preloaded with numbers, you'll have to go to second table set and make sure it's not on auto, it's on ask, and it'll look a little tiny different, but you'll see that it has like auto or ask for the independent variable. You want it to be on ask. Once you have that, then you don't have to change it ever again, because now you can type in a 2 and look at that, you get 48. What that's done is it's plugged in 2 and evaluated FP of 2, and that's 48. So that tells us right away that 2 is not a factor. It didn't give us a remainder of 0. The remainder was 48. So we're back to this, that 2 is not a factor. Great. So how do we find things that might be more likely to be factors? That leads us to like the most important theorem of this entire unit, which is the Rational Zero Theorem. This is pulled from the textbook, the old textbook. I'll stick it in the slides. It's very complex here. When you read it, you're like, huh, what? And it's because it's a generalized statement. But let's say you have a polynomial. What this is saying is that you can look at the first and the last coefficients of that polynomial, and those will help you find potential zeros that will work, that will let you divide out and continue factoring. So very similarly to, you know, when you had like a polynomial like that, you could look at like the product and sum. The product was related to the first and last. It had to do with that. It's not exactly the same thing, but that same idea of looking at the first and last. And essentially, all of your possible zeros will be fractions of the factors of that first and last term. So what that means is, let's say we had this again. I'm looking at this 3 and this -8. And they're saying it's P over Q, where P is a factor of A0 and Q is a factor of AN. So what that means is if we have that 3x cubed plus 11x squared minus 6x minus 8, I can look at factors of 3 and factors of 8 and any fraction made out of those factors. Okay, so we would write out all the factors of 8. We just look at the 8, and it could be plus or minus. So 8 has factors 1, 8, because 1 times 8, 2 times 4, and that's it, right? 3 times doesn't go in, 4 times is back to this. So any of these numbers plus or minus would work, as well as anything of that divided by the first factor. So the factors of 3 are 1, 3, and this looks like a lot, but trust me, they kind of reduce pretty quickly. So now let's just look at this. They say P over Q, right? So P is coming from the last term. So you start with these, and then any of those can also be divided by the factors of that. So it's almost like that's your fraction. So they might ask you at one point on Alex, write out all the possible rational zeros that you could have for this polynomial. And you're basically looking at all the possible combinations of these. So you could have 1, you could have any of these, as well as 1 over 1, which, you know, any of these over 1 is going to be just those. And then any of these over 3, plus or minus. I know that's messy, but you would write them out and you'd say, okay, well, I can have plus or minus 1, plus or minus 8, plus or minus 2, plus or minus 4. Those are all over 1. Plus or minus 8 over 3. And then you keep going. So plus or minus 2 over 1, which is already there, and 2 over 3, which is not yet there. Right? Do you see how I'm going systematically? I'm starting with each top number and dividing by all the possible bottom numbers. And then the last one is 4 over 1, which is already there, and 4 over 3, which is not yet there. So these are all the possible rational zeros, which means that, like, you know, x minus 1 could be a factor, x plus 1 could be a factor, x minus 8 could be a factor, x plus 8 could be a factor. So yeah, there's still a lot, but it's not like an unlimited number of things that you're testing. So now, knowing this, I can go back and I can test. Does 1 give me a remainder of 0? Does -1 give me a remainder of 0? Does 8 give me a remainder of 0? Does -8? And so on. So let's try that. Right, you go into y equals, and then you type in your function. So mine's under y3. Then I go to my table, and now I can ask it different values. So I can ask it a 2. 2 did not work. 2 was a possibility, but it didn't work. So it doesn't guarantee that it'll work. It's just things to check. Like I could check -2. -2 does not work either. 1. Oh, look at that. The first one actually worked. Right, so 1 gave me 0. So that means x minus 1 is a factor for sure. But sometimes, you know, you might have to keep checking some of the other ones. But once you find one, you're happy. And quite often you actually will find it quite quickly, even though it seems like there's so many choices. So now that I know that, let's go back to the polynomial. Because we checked p of 1 was 0, that means that x minus 1 is a factor. So you might want to just now practice your long division strategies, and perhaps you want to do the shortcut way of synthetic division. So if you get a 0 for your remainder, you know that you've done it right because the remainder theorem said it should give us a 0. So what that tells me is that this is my resulting factorization. So that this step actually tells me that when I convert p of x, I can factor the negative x minus 1 out, and what I'm left with is 3x squared plus 14x plus 8. I'm not done factoring, but now I've reduced it so that I actually have a square, a quadratic that I can now factor either through this process again. If I use the rational zeros theorem and I find a 0, I can just keep long dividing by the factor that I know is going to be there. I could also use the quadratic formula. I could use my regular factoring strategies of product and sum and splitting the middle term. I could, yeah, right? So you have lots of options once you're down to a quadratic. Let's see if this one's easy enough to find a product and sum for. So the product would be 3 times 8. 24, sum 14. I haven't done this one, so I don't know which way is easier. So we're just trying to use our toolkit on it. So can we think of a number that multiplies to 20, two numbers that multiply to 24, add to 14? Is that easy enough for us to find? Oh, 2 times 12. 2 and 12 make 14. 2 times 12 make 24. So I could do my like regular factorization process here, where I go plus 2x plus 12x plus 8, and then I do my grouping strategy. So x, 3x plus 2 plus, and then 4, 3x plus 2. So then that's just dropping down, don't forget about it. So I should get x minus 1, 3x plus 2, and x plus 4 as my factors. Now, there's a difference here between, so this is called a linear factor. Linear factors are, they start x minus something. And usually, like this is right away the 0. So this is a proper factor because it is actually 3x plus 2 to make it. But you could actually have this 2 over 3 as well, because those will produce the same zeros. This is because this is not exactly the same polynomial there, but it's because we're so interested in what are the zeros that, see, if you had done it this way, you would have gotten this. If you do it this way, you get this. We're not too concerned with the difference here because I know that my zeros, regardless of which way I got it, is 1, -2/3, and -4. These are my zeros for the polynomial. The only difference that this will make here is the shape of the graph will be slightly different. It'll be more accurate to this than if I have it this way, but we're not so concerned with that because we can always plug in a number and find the shape of the graph. So we're more concerned about the zeros. Okay, so now let's take a look at these zeros and look back at our list of possible zeros. So 1, -2/3, and -4. Were they all on our list of rational zeros? Let's see. -2/3 and I think it was 4. They're all on there. They will always be on there. But it just shows you that you only had 3 of those that would have worked. So if I had chosen a 4 or a -2/3 in my list, -2/3 and -4, right? So you just have many ways of cross-checking. So if you think of like the way you could study for this, if you were studying for this, is rather than trying to say, if this happens, then this happens, you need to almost like collect all the different strategies you have towards this whole concept. So for polynomial analysis or graphing, you have, okay, a table of values. If you get 0 in the table of values as an output, that means that's a remainder, that means that's a factor, that means you can long divide completely, and then you can use your factoring strategies to continue. So just for the purpose of argument, like if I didn't do this old process that I knew already, and I wanted to continue from here, I could have found another 0 that works for this new polynomial that I have here. And perhaps I would have found -4. So if I found -4, that means I could long divide that by that -4, or synthetically divide, and it should give me all the same result. Right? 3x plus 2, which is what is resulting after that. So this is fine, this is fine, the zeros are fine. And if our goal is to sketch it, now we can say, okay, 1 is a 0, -2/3 is a 0, and -4 is a 0. And if I'm sketching it, I see it starts with a positive, it's a cubic. Far left, a really big negative cubed is going to be really negative, so it's going to start here. None of these have been a higher multiplicity, so they're all going to just pass right through. So it should be something like that. And then obviously I could find more points by plugging into my table of values on my calculator. If I want to identify like a key point here, I could search for it on my graph a little bit to make it more accurate, but that's a sketch. As you go up, like as this becomes bigger, if that's a 4th power, we do this whole process again, but perhaps we have to do this process several times. So we could look at an example where we have a 4th power. Okay, so I want you to think about what you just experienced with that initial example. And remember, we took some detours here. We didn't need to do this. We didn't need to do this. This was the easiest thing to first look for. And in fact, looking for all the possible rational zeros helped us identify which one's going to work for sure. Okay, so try for yourself to use the Rational Zero Theorem, which was the one where you look at the first and the last number. We want to identify at least one factor or 0 that's going to work so that we can divide it out and continue factoring. so you start with the last one. The last one's on top, and it's always divided by the first one. So you would say, okay, that's a -4. So what are all the possible, I don't need the negative, but whatever, plus or minus 1, plus or minus 4. I always think like 1 times 4, 2 times, okay, well, 2 times 2, and those are all my possibilities. Okay, and for my bottom number, 1 times 6 or 2 times 3. And that's it. And now all of the possible combinations. So possible zeros, all the top numbers divided by 1, that just keeps them. Okay, and now divided by 6. And then 4 over 6 is 2/3, so I always simplify. And 2 over 6 is 1/3. Okay, and then all of them over 2. So 1/2 we don't yet have. 4 over 2 is 2, that's done already. And 4 over 3, not there yet. And then finally the 2, or everything divided by the 3. So 1/3, I already have that. 4/3, I already have that. And 2/3, I already have that. So those are all my possibilities for rational zeros. And now what I can do is I can start testing them out in my table of values for this function to see which one gives me 0, because that would mean that it's a complete factor with remainder of 0. So now when I go to my table, so now I can try all of those possibilities. Oh, look at that. The -2 gives a 0, right? Okay, does that make sense? So if -2 gives you 0, that means x plus 2 is a factor. And that should help us if we figured out, it doesn't matter which one you find first. If you found x plus 2 is a factor, that's great. That means that I can take my 6, 23, 19, -8, -4, and divide it by the -2, the 0 of -2, which is dividing it by x plus 2. If I pursue that, okay, so this is what I got. What is satisfying for me is that I do see that 0 and it cross-checks with the other piece of information I have, which is that if I plug in a -2, I should get 0. So having a remainder of 0 helps me see that this new polynomial is what's left after division by x plus 2. Okay. Okay, so now what that means is that I can say that x plus 2 times 6x cubed plus 11x minus 3x minus 2 is what p of x is. But now I have that second cubic there, which means that I have to do this process again. So if you see a fourth power, you're going to have to do it twice before you get down to a quadratic. And it's hard to, so the rational zero theorem should still apply because all of these were possible factors for the first one. Therefore, any of those should still work. You could do the rational zero theorem again for this. That'll reduce some of the possibilities, right? Because now you have a plus minus 1, plus minus 2 divided by possibilities of plus minus all the 1, 6, 2, and 3. So the only thing that's different is that I don't need to take anything that was 4 over something. But so, you know, really you're just testing a lot of the same numbers. So let's go back and test some more. So maybe let's try some of these. Let's try all the whole numbers. So all the whole numbers that were possible was 4, -4, which I already said those wouldn't work. So 2, -2, those don't work, and 1, -1. Well, the -2 already worked, so we already did that one. We can't use it again. Okay, so none of our whole numbers work, so we're into our fractions. So possibly 1/6, -1/6, 2/3, -2/3. And again, you're just searching, right? Yay! It's like you win the lottery. Look at that. It's giving you a 0. So -1/3 is a possibility, which means that x, so -1/3 worked. So if -1/3 worked, that means x plus 1/3 works. That means also 3x plus 1 would be a factor. So what I can do now is I can take this same resulting polynomial and I divide it again with that -1/3 as my divisor, 0, and I do the whole process again. Right, that'll get us down to a quadratic, and then that quadratic we can either use the quadratic formula or we can use continue it with this process or regular factoring. So let's do one more layer here, but this process is going to be very similar. So let's run through it here together. So 6, drop the 6, multiply by -1/3. So -6/3 is 2. 11 minus 2 is 9. Multiplied by -1/3 is -3. -3 minus 3 is -6. And -6 times -1/3 is +2, which gives us 0, which is good, which means that now we have this factored down to x plus 2 times x plus 1/3. Remember, it's opposite to the 0. And then 6x squared plus 9x minus 6. And so now we can use other strategies to factor this down. It's possible, if this doesn't factor, that you would run the quadratic formula on it. And that would give you the 2 zeros that would result. So when you're writing your zeros, you have 0 at -2, multiplicity 1, -1/3, multiplicity 1, and now you have another 2 possible zeros. So what's important to know is if it's a 4th power, you're going to always have exactly 4 zeros if you include complex numbers. Sometimes, like let's say this boiled down to something like x squared plus 9, which doesn't factor in the real numbers, but it does factor if you consider the i's. Like if you end up doing the quadratic formula and you get a negative under the root, that becomes an I, and that's where you get complex roots. So if you count those ones, you'll always have exactly the number of the highest degree of the polynomial. If you don't allow those, and those won't actually show up physically on your graph, but they are technically called zeros. So let's just try the quadratic formula on this and see if, maybe this factors nicely. So maybe you could do that. I'm just going to try this. -b plus minus b squared minus 4ac over 2a. And you have to kind of do all that. So let's see what we get for that root, because that's really going to determine if that's going to be a nice number or not. So 81, and then plus 4 times 6 times 6. I get 225. The square root of 225 is 15. So that does factor nicely. This becomes a 15. So I get -9 plus 15 over 12, which is 1/2. I'm doing some of this like without writing it out, but you can hopefully see what's happening. And then -9 minus 15 is going to be -24 divided by 12 is going to be -2. So you get another -2. So what that means is this one is multiplicity 2. So it'll bounce at that point. and it will pass through -1/3 and 1/2. And yeah, you could sketch the graph from that information. You can also write out this whole factorization then as, oh, and this was a, I guess, what was it, 2x minus 1 would have been the 1/2, and then the x plus 2 again. Okay, so then you can write out the full factorization like that, or you can write out the zeros that you have like that, depending on what they ask. Okay, so that's like a more complete process shown. And again, it's possible that when you do this last step, if you end up having a negative under the root, remember that a root of a negative is I. And so you would just call that I, and you would proceed with the I's for the two options, and you write them out like that. Yeah, so I mean, there's lots more examples, like some of the other examples, like this one's cubed. I think this one ends up having something where your final square term ends up needing the quadratic formula. So you'll have an answer like, say, maybe 1 plus √5/2 and 1 minus √5/2, like that sort of answer. That's possibility. I don't know exactly, but I think that's what I was going for there. Or that might be this one, actually. This one here, you'll notice you can factor out a factor of x right away, which reduces it to 6x cubed. So always look for common factors if you can. So that means that 0 is a 0. And then you're going to continue with this just like we did before. And I believe this last example would be one where once you get it down to the square term, that's going to produce something with i's in it. Maybe you'll have 5 plus I and 5 minus I, depending on what your quadratic formula gives you. And again, like I think before you do those, you really need to kind of work on some examples like this to follow that process. And so what I've done here is I've given you a bunch of examples here that you can try, and these are basically find all the zeros of the polynomials. So I would encourage you to just maybe practice some of these, follow what we've just done and practice those. And then once you do that, you'll notice I'll also give some examples that have answers with i's in them and see if that works for you. We can always cover that again if you have a question about it next class. And I mean, the last thing is like you will have some applications. For instance, if you want to get the volume of this box, you're going to go length times width times height, or the other way around. They want it to be 126. So I actually have to go in, multiply this all out, multiply it again, right? Get everything to one side equals 0, and then factor and find the possible zeros. Those zeros are going to be potential answers. You're going to have to interpret them based on the context. Again, very similar idea when we were reducing the size of that chocolate bar. Maybe you cut things down and you're slicing off 3-inch cuts. So you probably have like n minus 3 times n minus 3. And I think they've only cut 2 sides, so times n equals a 1560. And again, expand, get everything to one side equals 0, and try that out. See if you can solve for what the possibilities would be for that. And there's also like examples where there's like, you know, there's a polynomial that models a function of allergy medication, how it works in somebody's body between times 0 and 5. And so you might be asked, okay, something like, okay, so what if you have 30 milligrams of medication? At what times to the nearest minute does the level of it reach 12 milligrams? So this is already, that's the description of the function. So when does it reach 12? Your question is, when is it reaching 12 right there? So this one is a little different. Notice it has a calculator on it. So the ones that are more like with decimals and things like that, I'm going to minus that 12 equals 0. I'm basically interested in when this graph hits 0 now. And you might need a graphing utility to identify the zeros from something like that, because it's quite hard to like factor things with decimals in it. So this is more like a modeling example that uses some technology for it. Okay, so that's basically, I didn't show the complex examples, but it really is the same process. Like I'll show you, I'll throw this into the slides where it gives an example of one that has complex numbers. So they do all these processes. They find that the 2 works, they do that, then they take it down again. They find that works, so they're finding that the final thing they are left with is an x squared plus 4, which does not factor in the real numbers, but it does factor if you use the quadratic formula, a negative b plus minus b squared minus 4ac. I mean, you can do it this way as well, but if you're just kind of going through that way as well, you'll see that you have a negative 16 under the root over 2. And that negative root becomes an I. So that's a 4i over 2. Simplify, that's plus minus 2i. So that would be an example where it has complex roots or zeros. And you'll notice that they'll always have a conjugate pair. They'll always have a plus and a minus version of a complex number. So if you know that 2i is a root, then you know that negative 2i has to be one as well.